Welcome to The Explainer. Today, we're going to tackle one of those bedrock ideas in chemistry, balancing chemical equations. Now, I know, it might sound a little intimidating, but I promise you it's way less about complicated math and a lot more about solving one of the universe's most elegant puzzles. So, let's kick things off with a question that might sound a little weird, but stick with me. What do Legos and chemistry actually have in common? The answer, it turns out, gets right to the core of a fundamental law of the universe, and it's really the key to making this whole thing just click. And here it is. You can't just create new pieces out of thin air or make the ones you have vanish. Think about it. You've got a pile of Lego bricks, right? You can only build with what's in that pile. An unbalanced chemical equation is basically saying you started with 5 red bricks but somehow ended up with a car that has 7. It just doesn't work that way. It breaks the number one rule: matter cannot be created or destroyed. All right, here's what we're going to cover. We'll start with that core law, get to know the key players in any equation, and then I'll walk you step by step through the balancing act itself. We'll even get into some pro tips for the tricky ones before we wrap up with why any of this really matters. So let's dive right in. All right, first up, let's talk about the one rule to rule them all. It's called the law of conservation of matter, and literally everything we're about to do is built on this foundation. So our goal, our only goal really, is to get to this perfectly balanced state. A balanced chemical equation just means that the number of atoms you start with on the left, your reactants, is exactly the same as the number of atoms you end up with on the right, your products, no more, no less. Okay, so how do we actually get that balance? Let's meet the tools we're allowed to use, and maybe even more importantly, the one thing we are absolutely not allowed to touch. Okay, so you've only got one tool in your toolbox here, the coefficient. That's the big number you can write in front of a chemical formula, and it tells you how many of that whole molecule you have. Now, the subscript, that little number, defines what the molecule is. That little 2 in H2O is what makes it water. If you change that, you're not talking about water anymore, and you're breaking the rules of the game. Look, if you remember one thing from this whole explainer, make it this. You cannot change the subscripts. You can only change the coefficients. Seriously, burn this into your brain. It's the key to absolutely everything. Okay, now that we know the rules of the game, let's actually walk through our first puzzle together. We're going to use a super clear 4-step method that you can use for pretty much any equation you come across. It's a really simple process. We start with words, turn them into formulas, take a quick inventory of what we have, and then use our one tool, the coefficient, to make it all line up. Let's try it with a reaction between sodium and chlorine, which makes, you guessed it, sodium chloride, also known as table salt. So here it is, our skeletal equation. We have sodium, or Na, plus chlorine, which likes to hang out in pairs as Cl2, and that makes NaCl. Even just looking at it, you can probably tell something's a little off, right? Let's do a quick count just to be sure. And when we lay it out like this, the problem just jumps right out at you. Sodium's fine, 1 on each side. But look at the chlorine. We start with 2 atoms on the left, but we only have 1 on the right. That atom can't just disappear into thin air. We've got to fix this. So what's the fix? Well, we bring in our one and only tool, coefficients. To get 2 chlorines on the right side, we put a big 2 in front of NaCl. Perfect. But wait, that also gives us 2 sodiums on the right. No big deal. We just go back to the left side and put a 2 in front of the Na. Now, let's see where we're at. And voila! Look at that. Perfect symmetry. 2 sodium atoms on the left, 2 on the right. 2 chlorine atoms on the left, 2 on the right. Nothing was created, nothing was destroyed. The equation is officially balanced. Awesome. So you've got the hang of the basics. Let's level up. Not every equation is going to be that straightforward, so here are a few pro tips to help you solve those trickier chemical puzzles. Think of these as your secret weapons for the really tough ones. It's usually a good idea to save any single elements for the very end. They're super easy to fix. Same goes for hydrogen and oxygen. But the real time saver is this. If you see a group of atoms that stays together on both sides, just treat it as one whole chunk. And of course, always, always, always double check your final answer. Okay, let's put this to the test. Now, this equation looks a little messy, I know, but watch this. Do you see that group in the parentheses, the NO3? That's a polyatomic ion called nitrate. And the key thing is, it shows up on both sides of the equation. And this is where that pro tip becomes an absolute game changer. Instead of counting up all the individual nitrogens and oxygens, we're just going to treat that whole NO3 group as one single item, like a big Lego block. So we have 2 of these blocks on the left and 3 on the right. To balance them, all we need is the lowest common multiple of 2 and 3, which is 6. So to get to 6 on both sides, we just pop a 3 in front of the lead nitrate and a 2 in front of the aluminum nitrate. Boom, nitrates are balanced. Now the rest is a piece of cake. That gives us 3 lead atoms on the left, so we put a 3 in front of the lead on the right. It gives us 2 aluminum atoms on the right, so we need a 2 in front of the aluminum on the left. And just like that, we're done. Okay, your turn to be the puzzle master. Here's a challenge. Use the tips we just talked about, take a look at the elements, and see if you can solve this one on your own. Go ahead and pause here if you want to work it out. The answer is 2AlBr3 plus 3Cl2 yields 2AlCl3 plus 3Br2. Okay, so we've spent all this time on the how. Let's wrap up with the why. Because this isn't just some random exercise for chemistry class. This has huge real-world implications. What you really need to take away from this is that balancing equations, it's like learning the grammar for the language of chemistry. It's what lets us move from just kind of mixing stuff together to precisely predicting exactly what will happen. This is essential for everything from developing new medicines to creating rocket fuel. It's how we get the recipe right every single time. So at the end of the day, balancing an equation isn't just about making the numbers match. It's about understanding the elegant, unbreakable rules that govern how our entire world is built and rebuilt, one atom at a time. It's about learning to read the incredible stories that are written in the language of molecules.